Okay, hi everyone. Just doing a short sound check. Can you hear me? If you can hear me, just indicate in the live chat, just so that I know that I can begin. Can It's been a long time since we've done this, so yeah. Just double check. I think everything should be okay, but I'm just waiting for your response. Okay. Well, I guess I can begin lah. Okay, all right. Thanks, guys, for the response. But so today we're going to be talking about uh, interference of waves. Okay, which is the next subtopic uh, in this chapter lah. Okay, in this chapter of waves, I want you to know that uh, uh, I want you to know that when we go back to school, like if we ever go back to school, we will then only we will do all the experiments, all the lab activities that have to do with the four phenomenon, okay, which is reflection, refraction, diffraction, and interference. Okay, but for now we're just going to learn all the theories, and then we'll see what happens from there lah. Okay, so when we talk about interference of waves, so we've talked about the three first phenomena, which is reflection, okay, refraction, okay, and the last one is diffraction, okay, and interference is another wave phenomena, but it doesn't just involve one wave, okay. So I'm going to demonstrate this. I'm going to show this to you by showing you this video, okay, and take a look at this one. This video, I purposely turn off the audio because I just want you to see what's happening. So everybody knows what is, you know, what happens if you drop a ball into a water, okay? But what happens if you drop two balls, okay, into the water at the same time, okay? Or to make it even more interesting, instead of dropping two balls, okay, we have these two balls constantly hitting the water at the same time. Okay, let's take a look at what happens. So over here you have these two balls. Okay, ignore this guy. So these two balls, okay, are over here, and what he's going to do is, okay, so if you just have one ball, so this is very obvious lah. You make this ripple lah. Okay, you create this wave. But if you add a second ball with its own wave, okay, take a look at the pattern. Okay, notice that there seems to be a pattern where, okay, if you look over here, over here there seems to be this line over here. Okay, and if you notice from the original, okay, over here, in between the two faded places, right, there is this one very obvious, and it seems to be a stronger wave, okay, as opposed to the beginning. Okay, I'm going to continue to play and let's see. Okay, so notice that the two balls are going up and down at the same time, and you have this very obvious pattern. This is called an interference pattern. And actually, you can even do this at home. Okay, you can go to the toilet or whatever, or go to a lake that's nearby, and just do the bobbing up and down. Okay, you will actually be able to see this interference pattern. This is very nicely done. Okay, but this is what I mean by interference. Okay, and it must happen because there are two wave sources. Okay, previously everything is one wave source. You send one wave, reflect. You send one wave, refract. You send one wave, diffract. But for interference, you must have two wave sources. Okay, in this case, the two balls over here lah. Okay, and when the two wave sources send out their waves will interact with one another. The interaction of the waves is called interference. Okay, and for water waves, this is how the interference pattern looks like. it seems to be one blur and then one clear, one blur and then one clear, and then one blur and then one clear. Okay, notice that the blur lines are thinner, but the clear lines are the clear regions are much bigger. Okay, so this is just the beginning lah. I just want to introduce to you what interference is all about. Okay, and how it looks like. I notice that some of you cannot enter the. Okay, never mind. All right, so let's go and let's explore lah. Okay, what is the meaning of interference? Okay, by taking a look at this slide. So interference is the superposition, okay, of two or more waves from a coherent source of waves. Now there are two words in here which I need to explain. Okay, one is what is the meaning of superposition. Number two is what is the meaning of coherent. Okay, but basically, if you want to talk about it in simpler terms, okay, interference is just the interaction between two waves. Okay, but for the real definition, I know when two waves interact, okay, then what you can see is there will be the interference of waves lah. Okay, the waves will experience interference. But interference comes from the word interfere lah, macam mengacau. Okay, so they kind of like disturb one another. Okay, but the actual technical term, the actual physics term is the word superposition. Okay, when instead of using the word interact, kita guna perkataan superposition. Okay, dalam bahasa Melayu it's called superposisi. Wow. Okay, and then after that the other word is coherent. So what is the meaning of coherent first lah? Coherent. Okay, coherent is sources of waves with the same frequency and the same phase. Okay, or they are in phase lah. Okay, in phase means kalau one wave is going up and down, the second wave is also going up and down together with it. Okay, so these are coherent waves. Kalau one wave is going up and down, but the other one is going down and up like that, I don't know if you can see in the screen. Okay, those are not in phase lah, because dia bukan sama fasa. Okay, so this is same phase. So same phase, same frequency is coherent source. Okay, so I repeat, coherent waves are waves with the same frequency and the same phase. Okay, these two words must be in there. Okay, obviously it also has the same wavelength and the same amplitude and the same wave speed lah. But the most important is that it must have the same frequency and the same phase. Bila satu wave naik, the other wave also naik together. Bukan satu wave naik, the other wave turun, tiada. Okay, those are not in phase. Second word is the word superposition. Okay, so as I said just now, in the word, when we talk about interference, we don't say the waves interact actually lah. Okay, the waves don't interact, but actually the waves superposition. Okay, when the waves superposition, okay, they will produce an interference, and there are two types of interference, which is constructive interference and destructive interference. Okay, interference membina dan interference memusnah. Okay, so let me explain what constructive and destructive interference looks like. Okay, so this one lah. Okay, the principle of superposition says when two waves overlap, the resultant displacement is the sum of the individual displacement of the two waves. Okay, this is all technical, but this is actually what it means. So you have one wave coming in this way and the other wave coming in the other way, here like this. Okay, one is going to the right, one is going to the left. Somehow, when they meet together in the middle, they will superposition and become the total of both the waves combined. So kalau di sini dia punya amplitude adalah A, here also the amplitude is A. So during the superposition, it will be combined, 2A. So A plus A is 2A. Very simple, right? Constructive, membina. Dia mesti menjadi lebih besar. Okay? And then, okay, look, I want you to remember this, that the wave, after they superposition, they will carry on, They don't, like superposition and balik macam ni. From this picture, it looks like they are like bouncing back, right? Actually, it's not. They are going forward, going up, and then going on. Okay, as shown in this picture. Look at this wave P. Wave P comes over here before superposition. Masa superposition, it will combine together with wave Q, and after superposition, it moves on. Okay, and this is a very important thing. Dia bukan reflect balik tau. Okay, it's not reflecting. After interference, it just moves on. Okay, it's like a high five lah. After you high five, you move on. Nobody high five and then berbalik on. Tiada. Okay, after you high five, you will walk on lah. Okay, like let's say kalau ada dua orang yang berjumpa kan, lepas kamu high five, okay, nowadays we cannot high five lah because of COVID-19 lah. Or you berlaga tangan lah, okay. You high five berlaga tangan, then you move on ba, kan? You don't high five and then lepas tu berbalik. Doesn't make sense because you're going this way. Okay, so this is the thing that we must remember. Dia bukan berbalik, but actually lepas dia superposition, it moves on. Okay, and it's a very important thing to note lah. So, as I said before, constructive interference is one type of interference. Okay, so constructive is membina, destructive is memusnah. Kalau dia membina, bahkan it becomes a total of both the A plus A. But for destructive interference, this is another constructive interference. Tetapi the amplitude is going downwards. Okay, so this A and A. So if you notice over here, it combines and becomes a bigger one, 2A. But after that, remember, it still moves on. Okay. Now, for destructive interference, it's a superposition between a crest and a trough. That's the only way you can produce destructive. Kalau constructive, bahkan, is two crests combined or two troughs combined. Okay, but a destructive interference happens when like that. So this is what I mean. This P over here, after it destructs for a while, it moves on. Okay, it moves on. I know from this gambar aja kan nampak seperti this wave terus dia berbalik pergi bawah, bahkan actually it is not. Okay, what is actually happening here is this wave, after it destructs, it carries on. Okay, dia masih terus berjalan. So remember, waves always propagate. Waves always keep propagating. They never berbalik one unless it's reflection lah. But after superposition, after interference, the wave still propagates forward. Okay, very important point to note. Okay, all right. So those are the two types of interference: constructive and destructive. Remember that constructive is two troughs, two crests, but destructive is one crest and one trough. Okay, so as we mentioned earlier, this is an observation. If we did the experiment on the water, okay, this is how the interference will look like. Okay, and these are all the interference lines. Okay, but the point is this lah. If I give you this picture, how do you know which part is the constructive interference and which part is the destructive interference? Okay, is it is it these white and black lines? Are those the constructive or destructive? Or is it the regions, or this one where the wave is clear is constructive or destructive? And then this one where the thin line where it's blur, that's the constructive or destructive. Okay, that's what you need to know lah. Okay, so I'm going to explain. Okay, so in the water waves lah, okay, this is what we will see as I show you in the video just now. Now, the places where there are bright areas, okay, like over here, this is actually the two wave crests combined. Okay, the crest from here and the crest from here, when they when they superposition, they will cause this much brighter area. Okay, and likewise, so it is with the dark area. The dark area is where two troughs superposition, okay, and they will produce constructive interference. So we notice that this whole region here is where constructive interference happens. Okay, and this part where it's blur is because over here, okay, the crest and the troughs superposition to form a destructive interference. That's why you see it's always a little bit more blur lah. Because over here, okay, the waves are almost virtually gone. Sini, the waves are lebih kuat. Okay, because it's 2 times of an individual wave. Okay, and the other thing I want you to notice is this pattern. After one section of constructive interference, next to it, must be a section of destructive interference. Next to it must be a section of constructive interference, and then after that, destructive. Okay, so notice, constructive, destructive, constructive, destructive. Susah sudah sebut ni, destructive, destructive. Constructive, destructive, constructive, destructive. Okay. Okay, hold on. All right, so this is how it looks like in water waves lah. Okay, and this is the experiment which we will do when we go back to school. Okay, oh yeah, okay, but for light waves, this is how it looks like. Okay, so for light waves, so this part on the left here, okay, is one slit. Now you have studied this before. If it is one slit, this part is diffraction. Okay, hold on, I'm going to write this with pen. Okay. All right. So this part over here, okay, is diffraction. Oh dear, what happened to my writing? Okay, so here is diffraction, which is the, I think this is Adam's group yang menjelaskan pasal this diffraction that they, Adam and, oh dear, I can't remember who. Elijah's group. Okay, they explain about diffraction. When a wave goes through a slit, it will be spread out. Okay, so when it spreads out, then this diffracted wave we pass through two slits. Okay, and when the two lights, and when the two light waves pass through the two slits, the waves will superposition and will form this interference pattern where it's bright, dark, bright, dark. Okay, if you notice, bright, dark. Sorry, very fast. So the bright, dark are areas where interference happens. Okay, bright is constructive interference because it becomes brighter, and dark is destructive interference because it is the crest plus the trough, so it becomes very dark. Okay, so this is how we produce interference using light wave. So previously this one was water wave, okay, and this one is light wave. Okay, but the pattern is the same. You need to have two wave sources. Okay, you need to have two wave sources. Kalau water wave is kamu kasih goncang itu bola up and down. Kalau light wave, we have one light, but we pass it through a slit so that it diffracts, and then pass it through two slits. Okay, this ruang di sini, I repeat, this is called a slit. S-L-I-T. Okay, slit atau dalam bahasa Melayu is celah. Okay, so you have one slit over here. This here you have two slits. Okay, and we will see that when we go back to school. Now, so notice this okay, when you change the distance between the slits, okay, so this is one slit. So the bigger the slit, look at the pattern over here. Okay, what can you tell me about the distance between the slits and the distance between the interference pattern becomes thinner and thinner. I want you to notice this first. Okay, second one is if I change the wavelength. Okay, notice that if I notice which color is the one now where the constructive and destructive lines are much bigger. Okay, we find that when we use, which one is the biggest? Take a look. Okay, the biggest is red color. Okay, so we find now that red color, okay, has the biggest pattern. Okay, now we're just going to use biggest pattern now. I'll explain the actual meaning later. What about the smallest pattern? Okay, the smallest pattern is purple. Okay. Look at the pattern. The pattern very tiny, very thin. But red are very gemuk. Okay, the constructive and destructive patterns are very fat. Okay, yeah, so I'm just going to use biggest pattern and smallest pattern. Now, what is interesting here to note is that red has a very big wavelength and purple has a very small wavelength. Okay, that's why actually, if you think about it, that's why when we see rainbow, we always see red color first. Okay, because red has a very big wavelength. Okay, and because red has a very big wavelength, it is easier to refract. Okay, I tell you, big wavelength is very helpful one. Easy to refract, easy to diffract, and easy to interfere. Okay, much better interference pattern you can see. Okay, so the reason is this because red has a big wavelength. compared to purple. Purple has a very small wavelength. Okay. Also, for your information, our white color light, okay, the white color, okay, is actually a combination of 7 colors. The 7 colors of the rainbow, when you combine it all, okay, it becomes white color. So white color got no specific wavelength. Okay, only the 7 colors of the rainbow have specific wavelengths. And mengikut itu warna pelangi lah. Okay, red. Sorry, I remember it in Malay. It's Michael Jackson kena hantar balik India Utara. So merah, jingga, kuning, hijau kena hantar balik. Biru, indigo, and ungu. Yeah, I know. Sorry. Okay, so red has the biggest wavelength. Okay, and ungu, because it's the last color in the rainbow, okay, has the smallest wavelength. Yeah, I know. It's Michael Jackson kena hantar balik India Utara. That's all I remember. Since I was young, this is how I was taught to remember the colors of the rainbow. Okay, merah, jingga, kuning, hijau, biru. Merah, kuning, jingga, hijau. Michael Jackson kena hantar balik. Kuning, hijau, biru, India Utara. Indigo, ungu. Okay. Oh dear, my dog is getting very excitable. Okay. I will talk about this much later. So this is the interference pattern on the. Okay, this is how we do it lah. Okay, you have this laser pen and you have a double slit. I think we have a double slit in our lab. Okay, so hopefully we can see this lah. All right. Okay, so for now, I'm going to stop sharing this. I want to show you a couple of videos. Okay, just to show you the interference pattern. Hold on now. Oh, okay. Sorry. Actually, you know what? This is the one I wanted to show you. I forgot to mention sound. It's because we talk about water waves, we talk about light waves. I haven't talked about sound waves. So how do you produce interference in sound waves? Okay, remember, the wave sources must be coherent. Okay, so you have 2 speakers, okay, which is producing the same sound at the same time. Okay, and you put the speakers next to one another. Okay, now, what happens is that as you walk across the room, you will find that there is one section that is loud. The sound will be louder. And then one section that the sound will be softer. Okay, I know. Over here it says silent. Actually, it's supposed to be silent. Okay, if you follow the actual theory, okay, it's supposed to be loud and very loud and then no sound. Very loud and then no sound. Okay, just like our this one lah. So the one like this. Okay, if we use sound waves like water waves, this part here where it's constructed interference is supposed to be very loud, and then over here is no sound at all because sudah kena distracted. Okay, already destroyed lah. Okay, so it's supposed to be loud, soft, loud, soft. Oh, sorry, loud, no sound, loud, no sound, loud, no sound. Okay, but usually in actual life, what happens is it's just loud and soft, loud and soft, loud. Okay, but that's the interference pattern that you need to see. Okay, one section is louder and one section is softer. Okay, and that's the interference of sound waves. Okay, so I'm going to show you a couple of videos. I hope you can see the videos and I hope you can hear the sound. Please let me know if you cannot hear the sound. Because I tested this yesterday, it should work. Okay, but I want to show you this couple of videos just to show you how the certain things look like. Okay, so I want to show you this. Good job. Let me see. Okay, let's do this first. Okay, so this is in a ripple tank. Okay, so in a ripple tank. So this is how you will see this lah. Okay, so this is a ripple generator. If we were to do this in a lab, this is how it would look like lah. Okay. Oh dear, I need to move this. Okay, so you see the projection screen over there. Okay, so you have these 2 point sources, which like in the first video is like the 2 balls lah. Okay, you can adjust this one. So when it vibrates, okay, See, this is what happens. Of course, over here is difficult to see. Okay, you know, we need to turn on the light from above lah. Okay, which is how we did the reporting. And this is how the diffraction pattern, this is how the interference pattern looks like. Okay. So here the pattern is a little bit, you know, a little bit nearer to one another lah. Okay, the center over here is the constructive interference, and then you see there's this line over here. Okay, the line over here is destructive interference. Okay, so it's constructive, destructive, constructive, destructive. Okay, the more you do it, the more obvious it is lah. Okay, so this is an interference pattern. I really hope that we can do this lah. Okay, one day in the lab. All right, so that's the first video. The second video, sorry, please let me know please let me know if in the during the video if I'm talking but the video is also playing I wonder if you can listen to what I'm saying. Because if you cannot listen to what I'm saying then bagus saya diam saja dan suruh kamu tengok saja. Okay, the next one is light interference. Okay, I want to show you light interference. So this is how light interference looks like. But this one is a video combining both diffraction and interference. Okay, so you know what? I'm going to turn off the sound here because the sound is of no use. So the first one is a single slit diffraction. Okay, so you shine a laser through a very small slit. So this one is they're using a red laser. Okay, and a single slit, satu saja slit. Now in diffraction, we've learned that when a light wave passes through a slit, it will be spread. Okay, it will be spread, and this is how a diffraction pattern looks like. Okay, like this lah. So it's bright, dark, bright, dark, bright, dark. Okay, I hope that we can do this also lah one day in our lab. Okay, so here's the same pattern. Okay, when I make the slit increase, okay, take a look at this. Okay, the diffraction pattern becomes less obvious. Okay, dia macam dia kurang diffract lah. Remember, if you widen the width, this is Elijah's group lah. Elijah's group did this. When you widen the width, the diffraction becomes less obvious. Okay, as you decrease, the diffraction becomes more obvious. Okay, this is a very obvious diffraction pattern. Okay, you can see this. Okay, all right. Now, this is if you use pinhole. Pinhole is if you shine a laser in a pinhole, you know, satu lubang. It's not a slit. Slit is a one line like that, but pinhole is just one dot. Okay, and this is how it will look like. Okay, yeah, of course, it's very far away. Wait first. Okay, but when we go near, this is how a diffraction pattern looks like through a pinhole. This is a very obvious diffraction. Okay. The waves are spread out, so it's no longer just hitting one, but it is spread out like that. Okay, this is a diffraction pattern. All right. So now let's take a look at interference. Okay, double slit interference. Now this is 3 lasers with different wavelengths, but the slit is identical. Okay, so red laser, the second one is yellow laser, and the third one is green laser. Now, of the 3, red, yellow, and green, remember that red has the biggest wavelength. Okay, so biggest wavelength means the diffraction pattern, the interference pattern is fatter compared to green laser. Okay, and this is what we expect to see. Take a look. Okay, this is the red, that's the yellow, and that's the green. Okay, notice that. Okay, so just now what we saw, okay, notice that this one, kalau kita tidak zoom in bahkan, kalau kita tengok saja, this one looks like it's a diffraction pattern. Remember the diffraction pattern we saw earlier? It looks like it. But after the diffraction pattern has been interfered, okay, once you superposition, this is the actual interference pattern. Okay, and if you notice the red color is a little bit wider, okay, than the yellow, and which is a little bit wider than the green. Just now in the PowerPoint that I show you, it's, you know, they make it very obvious that the red is fatter and then the yellow and then the green. But in real life, the difference is actually very small. Okay, but there is a difference. Look at the red color, it's just slightly bigger than the yellow color, which is slightly bigger than the green color. But this is the diffraction pattern. Okay, if you remember just now, this is diffraction. Notice that there's nothing. There's nothing in the middle over here. But after you interfere, sorry. Okay, after you interfere, notice that even in this one pattern, other pattern kecil-kecil, there is a bright, dark, bright, dark, bright, dark, bright, dark. Okay, do you notice this? So that's the interference pattern in a light wave. Okay, is he going to zoom in some more? I don't think he's going to zoom in. Yeah, I think this is the maximum he can go. Oh yeah, okay, zoom in lagi. Wow. Okay, so this is the interference pattern. From interference lah. Okay, notice the difference between diffraction pattern. Diffraction is just one line, but interference, from far away it looks like one line, but actually this is the interference. This is one interference pattern. This is the bright. Next to it is the dark. Remember, when it is bright, it is constructive interference. When it is dark, it is destructive interference. Okay, so constructive, destructive, constructive, destructive, constructive, destructive. And then dalam pada itu, there's also this diffraction pattern. Okay, so it's pretty amazing. Just from that single slit, from one slit, one slit ka? Yeah, one slit, you can see two diffraction patterns. Sorry, you can see two patterns. One is the interference pattern, and the other one is the diffraction pattern. Okay, pretty amazing lah. And also very difficult to do. Okay, it's very difficult to do in our labs because number one, the wavelength of light waves is very, very small. It's much easier to do with water waves and sound waves because water waves and sound waves, the wavelength can be adjusted. The wavelength can be adjusted and you can listen. But for light waves, it's very, very difficult to do this successfully lah. Okay, because the wavelength of light waves is very small. Okay, walaupun the wavelength of red color is the biggest of them all, is still very small. It's like 10 to the power of -7, if I'm not mistaken. Okay, it's 0.0000, don't know what meters. Okay, it's very, very small. Okay, compared to sound waves and light waves. Okay, but of the three, I want you to remember that red is the most obvious interference pattern because the light wave of red color is the biggest of all the lights. Oh well, yeah, of the rainbow colors. Okay, right, let's take a look at another one, which is sound waves. Yeah, okay, sound waves. But this one, I'm going to let this guy explain because he has a pretty cool explanation. Plus, my voice is a little bit tired. Okay. Ooh.
So basically, this is the setup. The camera is going to be attached to this skateboard that I'm going to tape it on. And here is, this is a microphone that goes into the iPod, which is running a decibel meter app, which will measure the volume of the interference. And it's just going to be rocking back on the skateboard. And I've marked the spots of destructive interference with red duct tape. And the sound's going to be produced with these speakers, these two studio monitors that lead and go into this mixer. And it goes with a left and a right channel. And then you can control the volume here, and I set them equal. And here's the master volume. And then this USB goes to the computer where I'm running Audacity. And this second channel is panned all the way right, and this channel is panned all the way left. So yeah, and we're doing a frequency of 400 hertz, 440 hertz with a sine wave, and yeah, that's basically it.
Okay, so a decibel meter app is an app on the phone. Actually, you can download this app, and what it does, it measures the amount of sound lah in decibels. Okay, kekuatan bunyi dalam unit decibels. Okay, yeah, so this guy, what he did was he tried doing about higher frequency. Higher frequency means the sound pitch is higher, lah, like woo, like that, lah. Okay, just now the sound was just woo, like that, looked like pretty low, right? But he tried doing a higher frequency, and it was more difficult to get a reading, lah. Okay, so this is basically how sound waves now can be done. You can actually produce the interference of sound waves very easily. You can even, if you want, you can actually even replicate this experiment at home, but you need to have two speakers and connect it to an audio generator lah. Okay, audio generator can be done on the phone. Actually, I would want to do this in our school because it's pretty fun. Okay, and you can actually hear it yourself. Now, if you were listening to the video on your earphones, the pattern is more obvious. You can very obviously hear the sound becoming a little bit softer. As I said, it doesn't completely disappear. Theoretically, it's supposed to completely disappear. But because, you know, there's this sound coming in from the constructive interference next door, that's why it doesn't really completely disappear. You can still hear all this background noise. But the idea is there. You have constructive interference, bunyinya menjadi semakin kuat, and destructive interference, bunyinya menjadi lemah. Okay, and that's very important. So, in the case of our school hall, that's why we put the speakers on both ends of the hall. We don't put the speakers in the center. It doesn't make sense. Okay, and I will explain this in a little while. But by putting the two speakers there, and actually, if you do a proper experiment, you take a decibel meter app, okay, and then you walk from one end of the hall all the way to the other end of the hall, you will actually notice that there is a difference in the loudness of the sound. Okay, because of the constructive and destructive interference that happens over there. Okay, let me see if I have another video. Okay, I have one more video, but I will show this. Yeah, I won't show this yet. Okay, I want to show you the... Okay, so how do we draw interference pattern? Okay, so it's very simple. So you have two wave sources here, which are, remember, the wave sources must be coherent. Sorry. Apa ini? Okay, sorry, pen. Okay, so wave sources must be coherent. Remember, coherent sources are sources where the waves are same two things. What? Same frequency and same phase. Okay, so if you were to draw both patterns, you see something like this lah. Okay, where the yellow lines represent the crest and the non-existent black lines represent the troughs. Oh, okay, sorry, the dotted lines represent the troughs. Okay, now notice that when the two waves superposition, kau tengok di sini. Okay, let's say for example this dot over here lah. Okay, or this, okay, fine, this dot over here. Wow, so fast. Okay, so over here is this crest plus the yellow color crest. They superposition. So we know that when two crests combine, two crests from different wave sources combine, there will be constructive interference. Over here is two troughs. So constructive. Here also constructive. Here also constructive. Okay. Manakala, if you notice the places where the crest and the trough combine. Now see, this is crest and trough, right? Crest and trough combine, destructive. Here is the white crest and the yellow trough, destructive. Okay, here is constructive, here is another destructive. Okay, so you find that they are the destructive and the constructive kind of form lines. Okay, now these lines are what we call antinodal lines. Okay, where constructive interference happens. Okay, we call this antinodes. Okay, so tempat di mana constructive interference happens, okay, we call this antinodal, constructive. Okay, then tempat di mana destructive interference, we call them nodal lines. Okay, so nodal, okay, or nodes are places where destructive interference happens. Okay, so actually you find out that there's a line pattern over here lah. That's why in the wave picture that you saw just now, there's a region of constructive, then one line of destructive. Okay, because we find that all the crests and the troughs when they superposition, okay, they happen to form one line. It's pretty amazing lah. Okay, that even dalam superposition kan mereka masih lagi boleh membentuk satu garis yang cantik. Okay, so here's another one. Okay, so if this is a crest and a crest, this will be antinodal. Okay, and this is a crest and a trough. I don't know where's the trough bising though. Sorry, this is trough and trough, so it's also antinodal. And this is crest and trough, so this will be nodal lines. Okay, actually, it's not nodal, we call this nodes. Okay, and this is antinode. Oh, sorry, it's not nodes, it's node. Okay, the place where destructive interference happens is called a node. The place where constructive interference happens is called an antinode. The line that joins all the nodes is called a nodal line, and the line that joins all the antinodes is called an antinodal line. Okay, this is how you draw wave interference lah. Okay, all right. One last thing. Now, there is a formula that is involved when it comes to interference. Okay, and this formula explains three very important relationships. Okay, now, number one, this is the formula. Lambda, which is wavelength, equals to AX over D. Okay, A is the distance of separation between two coherent sources. X is the distance, it's very long. Okay, but basically it's the distance between two antinodes or two nodes. Okay, and then D is the perpendicular distance from the sources where it's very long. Okay, but I like to show it to you. Let me see. Oh, okay, fine. I want to show it to you using. Hold on. Okay, let me end this show first. I want to show it to you. I had a picture over here just now, but I don't know where it went. Oh, here. Okay. Sorry, I didn't know my presentation ended. All right, so this is what I mean. This is A, this is X. From one loud to another loud. From one antinode to another antinode, okay, is X. Okay, and this is D. D is the distance between the two speakers and the place where you take the reading from. Remember the skateboard thing earlier? Okay, the skateboard thing earlier is the two speakers is A. The distance between the two speakers is A. Okay, the distance between the speaker and the skateboard is D, but the distance between one loud sound and the other loud sound, which is two constructive lah. Okay, the distance between two constructives is X. Okay, so I would rather you remember how the A, X, and D is like from the picture. Daripada you remember, oh my goodness, what is the very susah? It's very difficult to remember. Okay, if you look at light waves, okay, this doesn't matter. This is the A. Okay, sorry, you know what? I'm going to share this. Can you see this? Okay, so here is the A. Okay, so the distance between this is A. Okay, the distance between the two sources. From here until the screen, this is D. Okay, now here is, sorry, this is very difficult. Okay, so this is the bright, right? Here is bright, and here is another bright. Am I right? Yeah, okay. So here is the dark. Now, the distance between two brights, okay, is the x. Okay, so remember the formula just now. The formula is lambda, the wavelength, equals to ax over d. Okay, so this is the A, this is the x. Okay, too bright or too dark. Doesn't matter, you can choose too bright or too dark also can. And this is the D. Okay, remember the formula this way. Remember the letters this way. Okay, daripada kamu susah-susah, actually it's very difficult to remember the actual definition. You know, the actual definitions over here that we just saw just now, which is like super long. Now, this one. Okay, distance of separation between two coherent sources. Distance of separation between is very panjang. Okay. Now, I want to continue from here to explain to you the three important relationships. Okay, from the formula, actually, you can derive these three relationships. The first relationship is A and X. We find that the bigger the A, okay, the bigger the A, remember this, A and X? Okay, so A is the distance between the two light sources, the distance between two speakers. X is the distance between two constructive or two destructive. So we find that smaller A has a bigger X. This is bright and bright. Bigger A has a smaller X. Okay, so this the distance between bright and bright is much smaller. Okay, so this is the first relationship. The bigger, sorry. Okay, we find that the bigger the A, okay, the smaller the X. Or likewise lah, the smaller the A, the bigger the X. Okay, the first relationship. Second relationship is wavelength and X. Okay, now as I said, red color has the biggest wavelength. That's why dia punya pattern adalah lebih gemuk, which you saw just now. So the bigger the wavelength, the bigger the X. Okay, or the smaller the wavelength, which is like this purple color, okay, the smaller the X. The distance between the bright and the bright and the dark is much smaller. The third one is the distance between the two sources and the screen, the D. Okay, so we find that the bigger your D, okay, the bigger the X. Okay, so D is much bigger. Kalau letak kau punya screen makin jauh kan, then the interference pattern will become much bigger. Okay, the distance between too bright and too dark, will become much bigger. The third relationship. Okay, so remember these three relationships, and it's actually shown here. Okay, everything has to do with X. Okay, kalau saya ubah this formula, you get that X equals to lambda D over A. Now, look at this pattern. If we want a bigger X, lambda must be bigger, D must be bigger, A must be smaller. Sebab ini adalah inversely proportional. This is directly proportional. The bigger your wavelength, the bigger the distance between you and the screen, and the smaller the slit, okay, will produce a much fatter pattern. Okay, the distance between two constructive and two destructive is much bigger. Okay, so please remember these three. I want you to remember the formula, and I want you to remember the three relationships. Okay, sorry, I'm kind of rushing because I only have 1 hour, and I kind of want to finish this today lah. Okay, so don't worry if you are lost and if you are like, oh no, this is too much information for me to bear. Don't worry. Okay, you can always take a look at this video again and repeat the parts which you don't understand. But I want you to remember this lah. Okay, three relationships. Okay, how do you Basically, if I ask you a question now, how do you produce interference pattern where the the distance between the two bright is smaller? So you want a smaller X. Okay, if I want a smaller X, this one must be small. Use purple color. The screen letak lebih dekat, and you make the slit much bigger. Okay, you make the slit much bigger, then you get a smaller pattern like this. Okay, so you need to know how to use these relationships to produce the pattern that you want. Okay, lastly, is the application of interference of waves in daily life. So, you know what? I'm just going to show this video to you.
Have you noticed how a lot of ships have this strange protrusion at the forward end? It's a big lump of metal sticking out below the water, and we call it the bulbous bow. But it serves a specific purpose. In this video, I'm going to tell you what it is for and why they are fitted. Looking at these different pictures, you can see the ships are all different sizes. Just like the ships, the bulbous bows are also all different sizes. They're all designed specifically for the ship in which they are fitted, and they're all designed to serve one main function. To understand a bulb, let's first consider this vessel which does not have a bulb fitted. As it moves through the water, a pressure wave builds up at the front of the ship. This increases the height of the water. The ship is pushing it ahead, but that water has to go somewhere. So what happens? It flows back down the side of the hull. It will keep flowing back down, forming this wave all the way along the side of the hull. Now the problem with this is it increases the drag of the vessel. It's in contact with a larger surface area of water. It's coming higher up the hull. The water is moving at an inconsistent speed because it's going up and down as well as along. This increases the fuel consumption of the vessel. We need to find a way to mitigate this wave. We can model this wave mathematically. On this graph, I've plotted a curve of y equals sine x. If we think back to mathematics, we also know if we plot another curve that is 180 degrees out of phase with our initial curve, then they will actually cancel each other out. All you do is you add up each of the points along the curve, and the resultant is this line straight through the middle. If we could generate the same thing on a ship, we would be able to mitigate that wave that's causing all that drag. Let's now return to our original ship diagram. I've now taken it out of the water so you can see the shape of the hull underneath. We zoom in on the bow area because that's the area we're interested in. I can do a quick redesign and add a bowl and change the underwater shape. This is going to affect the way the water moves around the hull. If we think back to the original waveform, I can overlay it here in blue. This is the effect that the hull itself has on the water flowing around it. But we've now got this additional bulb at the front. So what I can do is I can overlay the waves generated by that bulb alone, and I'm going to put them here in red. Now you'll notice that these two waves are out of phase with each other. And what we just went through with the maths, we know that those waves can cancel each other out if they're out of phase the correct amount. In this case, they are. And what that does is that flattens out the waterline along the full length of the hull. It does mean you still get that slight uprise here at the bow, but along the majority of the length, the water is now flat. This has reduced the drag and it's reduced the fuel consumption. And this is the main reason for fitting a bulb. If we remember back to the start of the video, we saw that old bulbs are different. They're designed specifically to produce that wave 180 degrees out of phase to reduce the fuel consumption on their designed vessel. Anything outside of the design parameters, we're talking speed, loading conditions, hull size, the bulb will no longer work, and it would actually increase fuel consumption because it's an extra lump of metal that the ship is having to carry around. If it doesn't produce that useful wave, it's no longer any good. And that brings us to the end of today's video. Hopefully you found the information useful. Until next time, thank you for watching and goodbye.
Okay, so basically this bulbous bowl okay, what it does is it produces another wave, which if you heard the video just now, it says out of phase. Oh, sorry. Okay, out of phase. Out of phase means they're not coherent. Okay, so if you have the wave of the water coming one way, and then the wave that is produced by this bulb over here, it is out of phase, not coherent. Okay, what's going to happen is there's going to be destructive interference. So when the two waves superposition, there will be destructive interference. Okay, and then what happens is it helps the boat to move faster lah. Okay, because if it's already hard enough to go against the wave, but if you are actually being stopped by the wave, there's a lot of drag over there. Okay, and it's not good for the ship because you waste a lot of petrol just overcoming the drag. Okay, the next one is this anti-reflection glasses. Okay, those of you who wear specs like me, so this is kind of like, wow, latest technology. Okay, how does anti-reflection means you cannot see your reflection on the mirror. The other day I was having a video call with a friend lah. Okay, but the problem is the friend's phone was down there. But you know, even in the video call, then I asked my friend, "What are you doing?" He said, "Nothing. I'm listening to you." Then I saw the reflection on his glasses. I said, "Hello, you're messaging somebody." Okay, it's because I saw the reflection in the glasses. Okay, but nowadays we have glasses that are anti-reflecting. Okay, and it is also because of destructive interference.
After your eye health exam and you've found your perfect eyewear frame, you now have an array of lens options to choose. With the digital age, the most important option is an anti-reflective lens, also known as AR. This feature has many benefits to help anyone wearing glasses. The modern lens materials have a higher refractive index than previous materials. These modern lens materials can produce a stronger prescription with a thinner and lighter lens. However, they are more prone to reflection and glare. AR will reduce the glare. Premium AR will also strengthen and harden the lens material to prevent damage. If you drive at night, you probably notice the headlights of other cars make it harder to see. An anti-reflective lens reduces the amount of glare you encounter, which can make you a safer nighttime driver. AR lenses also benefit computer users. Glare from computers can cause extra vision stress and add pressure to the eyes. AR lenses can help computer users by causing less irritation to their eyes. Another benefit is that AR lenses let in more light. This feature allows better vision with higher contrast and clarity, especially in dim settings. AR lenses also make you look better by reflecting light to see more of your eyes. Without the glare, people would be able to see your eyes more clearly, even when taking pictures. Speak to an eye care professional to talk about your AR lens options that are suitable for your lifestyle and visual needs.
Okay, so yeah, so if you ever want to have a career in making spectacles, you know, why not lah? Okay, so AR lenses, I know that in our class, Wilson has a AR lens because it's the same as mine. Yang kita bilang kan dia pandai menjadi hitam bila terang, bahkan. But that's an example of an AR lens. Okay, but of course, Wilson's one is very high class AR lens lah. Okay, yang boleh menjadi hitam. But basically, you cannot see the reflection. Okay, and this is done by interference. Okay, so the light wave is one wave, and then the glasses help to produce another wave which is out of phase, so it's not coherent. Okay, last one. Sorry, I know this is very long. Last one is noise cancelling earphones or noise cancelling headphones. Okay, now whenever you see the word cancelling, then you know the interference that we want is destructive interference. So you have the noise from outside. I don't think there's a video here. Yeah, there's no video here. Oh, there is a video.
Hey guys, I'm Jason with Sonic Electronics, and noise-canceling headphones are one of the most popular types of headphones on the market. They are ideal for environments with lots of background noise, and they give you the peace and quiet you need to get through that tough project or activity. However, few people understand exactly what noise canceling is or even how it works. So if you're curious about noise-canceling headphones, then you've come to the right place. This technology aims to rid the excess ambient or background noise that prevents us from fully enjoying our music. In other words, it makes the noise level inside the headphones much more quiet so the music can be heard much more clearly. There are two different types, active and passive. Active noise canceling utilizes a power source to reduce the outside noise and is more effective at lower frequencies. They are usually more expensive because there's more technology implemented into the headphone. On the other hand, passive noise canceling uses insulation and sound absorbing tiles and is typically more effective at frequencies above 2000 Hz and does not need a power source. Now, active noise canceling technology seeks to cancel out the background noise instead of trying to physically block it. Here's how it applies to headphones. Sound travels through the air in the form of waves, each with a particular shape. This is where the active noise canceling technology comes in. It has small microphones that detect the frequencies in a given environment. The digital processor then determines which sound waves are required to cancel the unwanted sound wave, and then amplifies it through the headphones. To put it simpler, imagine a positive sound and a negative sound created at almost the same time. These sounds cancel each other out and bring the listener closer to a level of total silence. A good noise-canceling pair of headphones should be able to reduce the background noise by up to 80 dB, which is equivalent to about the level of a jet engine inside of an airplane cabin. Noise-canceling technology has been around for quite some time, and the technology has drastically increased over the years. As a result, there's a wide variety of noise-canceling headphones that can fit almost any application. So why should you continue living your life in a hectic environment? Pick up a pair of noise-canceling headphones today and let your ears listen in peace. I'm Jason with Sonic Electronics, your source for anything and everything headphones.
Wow. Okay, so yeah, so that's basically how a noise cancellation headphone works lah. Nowadays, even earphones have noise cancelling technology. Okay, that just shows you how amazing technology is lah. Okay, inside there's a digital processor which can produce a wave to cancel out the outside punya bunyi. Okay, by producing destructive interference, so that you only hear the sound that you want to hear. Okay, and this is especially if, like for me, like whenever I travel on a plane, the noise of the plane is pretty noisy. Even inside the plane, it's pretty noisy. But when you put on a noise cancelling headphone, okay, good noise cancelling headphones will totally cancel out the sound. You only hear the music that you want to hear. Okay, and it is done by destructive interference. Okay, so if you want to watch these videos, actually these videos, the QR code is in your textbook. Okay, so you can just view it lah. All right, one last thing before I go, I just want to show you your homework for today. Yeah, okay, it's a very simple homework. If you have not finish your homework before this, hello, please finish your homework, okay? Jangan juga mengada. Okay, your homework for today is, wow, I can't find it. I don't know where it is gone. I had the homework here just now. Okay, anyway, your homework here is in your textbook lah. Okay, I think it is page, oh no, I must have made it disappear. Okay, never mind. Please answer page 219. Okay, page 219 in your textbook. There's only one question. Okay, so it's a very simple homework for this week. Okay, page 219, formative practice 5.6. Okay, answer the whole of question 1. I will give you the link to send your work in the Google Classroom later lah. All right, sorry for taking 5 minutes extra of your time. But if you don't understand anything, you can always ask me, or you can always watch this video again. Okay, please don't forget to like, share, and subscribe. Okay, this video. I will see you all in the next class. Okay, take care, everyone.